let's begin. So today our speaker is Riya Dogra, and she will tell us about the Jones Polynomial and the von Neumann algebras. Please.
All right. Is this visible to everybody?
Yes.
All right, great.
Well, but actually, I see only a little picture, but not the big screen. Maybe it's only my problem.
Yeah, maybe you could try and pin the video.
Well, just a moment.
Yeah, sure.
Oh, yeah, that's it. Yes, please.
All right. So we begin by the definition of a von Neumann algebra. A von Neumann algebra over a given Hilbert space H, it's a star subalgebra of the bounded operators on H, and it needs to contain the identity operator, and it should be closed in the weak operator topology. Now, first of all, we're studying von Neumann algebras to arrive at some relations of projections, which we shall then relate with those of Markov for braid, so that we can form a sort of equivalence with some adjustment to form the Jones polynomial. For that, we need something known as a factor. Before a factor, we define what a commutant is. So if you have a subset of the bounded operator set of Hilbert space, then we define the commutant like this. It's all the elements that commute with A, and the bicommutant as the commutant of A, commutant of the commutant of A. Now, a factor is, first of all, it's a von Neumann algebra, and its intersection with its commutant needs to be some scalar multiple of the identity operator. Now, there are many kinds of factors. For example, type 1, which is nothing but isomorphic to this set, and type 3 are a bit too exotic for our use right now. So we shall focus on what's known as the type 2-1 factors. And before actually defining what a type 2-1 factor is, it's useful to look at how they're constructed. So we'll construct them in the form of group factors. So what we do is, first of all, we take a discrete group G, and we define the group algebra over the complex numbers. This group algebra is all the set of all possible finite sums, where this is the Kronecker delta function, and alpha G is a scalar multiple. And for example, if you have the infinite dimensional case, then we need to complete this set to L2G, which is given like this, and we complete it to a Hilbert space, and the inner product is given by the Kronecker delta function, which is 1 if the group elements are equal and 0 otherwise. And from L2G, the inner product looks something like this. It's the first scalar multiple into the conjugate of the second one. All right, once we have this into place, now we want to define what's called as the standard representation, and it's also known as the left regular representation. We define it something like this, where when you take an element in this algebra, it goes to this element, where lambda G is defined as, where lambda G acts on an element delta H, and it just acts by left multiplication of the group elements. And this is called the left regular representation. Now, because we have this identity in place, it holds that all the lambdas, all the group acts, all the actions that we have seen, they are unitary operators. And this is a sort of a verification, because the star element is given by the inverse, which gives you the identity element, and similarly for the other combination. So from all this, for now, we know that when we have all the finite sums, the set of all finite sums, and we have the left regular representation, then they are nothing but the bounded operators on L2G. And now this set is very important for us. We define capital LG as the closure of this representation in the bounded operator set of L2G. Now, this element that we've just defined, it's called the group von Neumann algebra, and it has a natural associated trace, which is given by this formula. And it's easily checked for group elements G and H, and by linearity, we can extend it to the entire LG. Now, since we already have a von Neumann algebra in place, now we need to show that this is also a factor. Now, this is a type 2-1 factor if and only if G has infinitely many conjugacy classes. This happens because for an element, for such an element to lie in the center, it needs to be constant on all conjugacy classes. But when we have the conjugacy classes as infinite for every element, then this scalar has to be constant, or a scalar multiple of the identity operator, and which is exactly the condition for a factor to be a type 2-1 subfactor, type 2-1 factor. Now, to also we also need the commutant condition in place. So for this left regular representation, we define the commutant, and that is nothing but the right regular representation, which multiplies the Kronecker delta element H with the inverse. Yeah, and similarly, once you have this right representation, you define R of G exactly like we did with L of G with the closure of this representation. And because it also needs to be a star algebra, we have the antilinear star operation denoted by J, and it takes any element in that algebra, which looks something like this, to this element, where the scalar multiple goes to its conjugate, and the Kronecker delta of G goes to the Kronecker delta of G inverse. And a very simple calculation implies that this identity holds. And by virtue of this definition, we have some properties for LG and RG. The first important property is that they both commute. And the commutativity can be checked, first of all, on the group elements G and H, which is easy to check, and then extended by linearity to LG and RG. And by the definition of the commutant, because the commutant is nothing but the right representation, we have this order. LG is a subset of the commutant of the right one, and the right one is a subset of the commutant of the left one. Not just that, the equality holds here because of our star operation, in particular because of this identity. All right. So now what we've done is we've constructed a type 2-1 factor by using this by using a group. Now all we need to know to actually have a concrete example in hand is to have a group which has infinitely many conjugacy classes. And the simplest example for that is the group S infinity, which is nothing but a finite permutation of infinite elements. And because it has infinitely many conjugacy classes, so L of S infinity, constructed exactly like we did before, it's a type 2-1 factor. And an even better property of this exact factor is that it's hyperfinite. It just means that there exists a star sequence, a dense star sequence in L of S infinity. Now, what's even better about a hyperfinite 2-1 factor is that there is only one such factor, and basically every other such factor is isomorphic to L S infinity, and so which is denoted by R. All right. So now that we have our terminology in place, what the next thing we want to do is we want to know how the subfactors, they sort of look inside this LG space. So for that, we need to have an idea about their sizes. Should I erase this one? So to see the relative sizes of a factor M and its commutant in the space that they lie in, we will define something called as the Jones index. And to reach there, we first define the dimension of one factor with respect to the other. All right. So to define the dimension of M, we shall define it by the trace of a particular projection, and that projection is given by an isometry. So if M is a type 2-1 factor and H is a module over M, which is also a Hilbert space. So this isometry is given by this. Now, why we are looking at this is because when we have such a representation and we construct a module over it, we can sort of take one factor and either amplify it or reduce it by means of projection. So this is nothing but probably an infinite case of a direct sum of the module formed by H. I don't need this right now. Okay, so the significance of this theorem is that if you have any action of M on H, then it is given by, it is equivalent to the action of a projection on this space.
Riya, I'm sorry to interrupt, but could you please explain us what L2 of M is? I mean, big L2 of M.
Yeah. All right. So herein we constructed L of M, and yeah, it's the same. It's the Hilbert space completion of the left representation of M.
Okay, but this is what do you mean by completion? So M acts on well, M is not as do you assume that M is the group von Neumann algebra, which was defined before? So in the theorem, you
yes,
in the two factors. So do you mean that M is the von Neumann algebra?
I'm sorry, I cannot. I can't hear you. There's a lot of noise. Sorry, could you repeat your question? I could not hear it.
Okay, so do you assume that your von Neumann algebra, that your 2-1 factor is the group von Neumann algebra which you defined before?
Yes.
Okay.
Because it was found by the, so it's just L2M is the standard representation of M, which was the group one Neumann algebra that we found earlier. And to see what it looks like, it also has an involution, the J that we defined earlier on LM. So it is the involution of this space. All right, so now that we have that, Okay. Yeah, so now that we have this isometry in place, we define the dimension. It's also called the coupling constant or the M dimension. And now an important fact to note is that this trace can take any values in this interval. And this happens because this vector here, it lies in the commutant. And a commutant that looks like this, where M is a type 1 factor, and that is a type 2 infinity factor. And by the properties of that, we have that the trace can lie anywhere between 0 and 1. All right. Now, there are some properties of this trace which I might have to state later. Okay, but before that, let us define the Jones index. So now Jones index is defined for two factors, one of which is included in the other, and they're both type 2 1. And they're defined with respect to as this number. It is the dimension of n, and it is the size of it is seen as relative to the left regular representation of m. And as seen before, this number can be any number that ranges here. And one also very beautiful property of Jones index is that we just looked at one type of construction for the type 2 factors, but no matter how you construct a type 2 1 factor, this will always result to be an integer for an integer. I'm sorry. For this, it is greater than or equal to 1. Now that we know what it is, now we want to know what exactly these numbers are and how they're attained. And for that, Jones gave another theorem. The proof of this theorem is where we will finally begin to see the relation between von Neumann algebra and the braid algebra. So although we won't prove this theorem, but we would discuss a part of the proof, which is the construction of the Jones star of projection. First of all, we state it. So for the first part of this theorem, it says that if the index, we know we have a bound for the index, then we have an explicit formula to calculate it. And for that, there exists an integer n greater than or equal to 3, such that the index is nothing but this. And for the second one, let M be a hyperfinite, the subfactor that we've been working with before. Then not just this formula holds, but not just that. If you take any real number that's greater than 4, you will find a subfactor and such that its index is equal to this number. Oh, I'm sorry, the index is equal to R. So all of those numbers are attained as indices. Now, shall move on to the Jones star.
Can you repeat about Jones index, the meaning of it?
Oh yeah, sure. So the Jones index is the dimension of n in this space, in the left regular representation of M, which we extended to a group one Neumann algebra. That's how Jones index is defined. And the bounds for numbers are given by the Jones theorem here. And now we construct a sort of star of subfactors using this. All right.
So index shows us the dimension of representation. Yes.
The index shows you how this subfactor fits in the representation for M. It is kind of a unit for size, to see how the sizes relate for the subfactors that lie in, for one that lies in the other. I will.
And it can it be an integer fraction?
I'm sorry, what?
Can it be fraction?
Can it be a fraction?
Yes, because according to A, we have formula.
Yeah, it can be a fraction. In fact, not just that, if you have any fraction that lies above this, you will have n that will attain that fraction as an index with respect to L to M.
It is not necessarily rational, of course, because the trace, which
Yeah.
is economical trace in our algebra, is real valued on the positive elements. So when we apply the trace, you get something real, but not necessarily integer and not necessarily rational. So this is just a real number.
But we talk about dimension of representation.
The dimension is defined in terms of the trace. The trace is, in general, is real valued.
Here, the dimension is defined with respect to the trace, and this the trace of this operator, it is the isometry that was given here in this theorem. Just in case.
We have non-integer dimensions, yes.
I'm sorry, could you repeat?
We have non-integer dimensions.
Yeah, there could be integer dimensions.
We do.
All right. All right. So this is called the basic Jones construction. So if you have two subfactors and the index is finite, then we denote the orthogonal projection onto of L to M onto L to N as En, and then we define M1. We just put M1 to be this element, which is the algebra generated by the M and the projection En that we started off with. It's the bicommutative, and it's clear that it is a subset of the bounded operators on L to M. Now, once we have this, we are going to denote it like this. So M1 is the algebra that is generated by M and En. And in the same way, we can form M2. And for this algebra, the trace, for example, for M1, the trace is given by the trace of the projection that we used in generating the algebra. And it also holds that this value, it's nothing but the inverse of this index. We started off with a finite index, and then this value is nothing but the inverse of that index. And using this construction, we can just repeat this construction and then have a tar. Okay, so if I have to formally state the Jones star, I will just mention it here. All right. So now that we have the construction of a Jones star in this, what we need to look here is that we get a sequence of projections which come with in the generation of every subsequent factor, and that sequence is called the Jones projection. Why we're looking at this is because they behave very nicely in the sense that they follow some really nice relations which relate very closely to those for the braid groups, and also Markov's relations for the equivalent, the invariants of braid. I should just write down those relations here. All right. So these are the relations that the sequence satisfies. And if all these, for now, we just know that these are Vaughan Neumann algebras that we've created. But it turns out that for the hyperfinite factors, all of these are type 2 factors. And for that case, there is an additional condition that the trace satisfies. And that condition is this, which means that if you have an element which is generated by, which lies in the algebra generated by this set, then if you add another generator to it, it's nothing but constant times the trace of itself. And this property, it is related very closely to Markov property 2. We shall go on to that next. All right, now that we have these relations in place, we want to know what, so we're doing all this to define a polynomial, an invariant polynomial on braid and analogously on links. So now let's see what those look like.
So what we defined, is it related somehow with Hecke algebra?
Yes, it's very close to Hecke algebra. Yes, you're right. In fact, through Hecke algebra is where the idea for the normalizing constant came. Also, another thing to notice is that using the relations that we just got before, they are enough to calculate the trace on any word formed by the sequence of Jones projections purely algebraically. And this fact will be useful to actually evaluate the polynomial that will be defined later. All right. So now we need to discuss the concept of braids and links. All right. So starting with the link, a link is nothing but a closed curve in 3 dimensions with no self-intersection. And because it's a sort of purely geometrical object, it's easier to study links by use of the braid group, and that happens because of Alexander's theorem, which states that any link can be formed as the closure of some particular braid. So for that, we need to see what a braid looks like. I'll draw it first. All right. So this is an example of a braid. This is a braid on 4 strands. What happens is you take 2 bars, and you can look at a braid. It's like 4 particles that move down to one of these points, such that at no point of their journey do they turn up. So this is what a braid looks like. And a closure of a braid is nothing but if we just sort of join these points together without any additional crossings while joining. So this is a closure of a braid. So if you have any link here, it can be given by the closure of some particular braid. for example, for this link, it's not very clear, but these three crossings correspond here. And then when we close this braid, it is nothing but this knot. It's also called the trefoil knot. All right. Now, given any braid, okay, suppose now take a set where the set consists of all possible braids given on n strands. Now this set forms a group under the operation concatenation. It's nothing but you take one braid and sort of put it under the second one, and the motion continues where you connected it. And the inverse is given by the mirror image. And Artin gave a very nice looking presentation of the braid group. Oh, before Artin's presentation, we need to know that this braid group n, it can be generated by n-1 generators. Let's denote them as sigma I, and sigma I is nothing but a braid of this form. Yeah. All right. So we have generators like this, and if you take any braid, it is given as some combination of these generators. And now Artin gave a presentation with respect to those generators. So any braid group can be generated by n-1 generators, and they have to satisfy these two properties. This is the Artin's presentation. And already using these two relations, we can see some connection with what we have here. Now, we need this relation to have an invariant with the one from Artin. And somehow this trace is going to help us get that normalization constant. All right. Oh, okay. Also, whenever we represent any given link in the form of the closure of a braid, that expression in terms of braid generators, it does not need to be unique. In fact, it's highly non-unique. There are many possible representations. So Markov's theorem sort of gave an equivalence relation so that we could understand the isotropy of two equivalent braids. All right, so if alpha is a given braid on n strands, then this type of move where you conjugate alpha with any other element from the braid group on the same number of strands, then these two elements are isotropic, they're sort of equivalent. And the type 2 move also gives equivalence, that if you have a braid that's generated by n-1 strands, then if you add the nth generator or its inverse, it does not change the braid. All right. So now the similarity that you see between these relations, it sort of motivated Jones to look inside the representations for braids and in the properties of the subfactors to find out some invariant. And so in fact, if we have a given braid group Bn and the algebra generated by those projections that we saw earlier. I can just write in. Then we make a particular substitution. All right. So this particular substitution is also, if any of you have seen the Potts model in statistical mechanics, and when we take a Q-state Potts model, we do a very similar substitution to get the Jones polynomial through that model. And that it actually came from the idea for that substitution, it came from here. All right, the relations that this satisfies are due to this substitution, we have this relation which exactly corresponds to that for a given braid. Similarly, this one corresponds to this one. Okay, I am so sorry. If I sort of did not use the correct notation here. These are the braid generators. So these are all sigma i's, not ei's that we've seen earlier. These are sigma i's and braid generators like I showed you before. Okay, there's no. It's also satisfying an additional relation, but we do not need it for the equivalence. Before that, All right. So using the GIs that we've defined here, with respect to this substitution made, if we associate to every GI the braid generators that we have here, then we get a representation of a braid group on n strands inside the algebra that is generated by the projections, n-1 projection, along with the unit. All right. And these are some properties that this representation satisfies. All right. So now what we need to see is that our candidate for an invariant is the trace of this representation of the braid group inside the algebra that was generated by the projection. So that should give us an invariant for links. In fact, it actually does turn out to give us an invariant, but with a slight adjustment. And so therefore now I define the Jones polynomial. All right. So if you have any link, any oriented link L, which is just a link with some decided orientation, and that link is given by the closure of some braid, let that braid be called as alpha, then the Jones polynomial is given by this expression. And here the exponent sum of alpha here as a word with the braid generators is E. All right. And it also, this polynomial has some very nice properties. One of which is that it is very sensitive to the mirror image. If you change this variable, if you make the substitution t to t inverse, then the polynomial that you get, it's mostly the polynomial for the mirror image of the link. And it's not a complete sort of invariant, but it is relatively very powerful as compared to the other ones that we have. All right. And so for an example, the link that we saw earlier, the trefoil. So as the representation of a braid, it is sigma I. It's written as the cube of sigma I, and the sign depends on the orientation and what sort of crossings we're taking. And This lies in the braid group B2. And using this formula, and so if you take there are two kinds of trefoils, the left and the right trefoil, and they are mirror images of each other, but they're not equivalent, as in they can't be taken from one to the other using some moves which are called rider master moves, which basically those are the only three kind of moves that are allowed, so that whenever you use those moves, the braid is still equivalent to the one we started with. And they're not equivalent, and this is just an example. This is for the right trefoil, and for the left trefoil, it is done by the variable change to the inverse of t. Yep, and that's it. We have obtained the polynomial. Does anybody have any questions?
Yeah, I want to ask about connection with indexes we defined.
I'm sorry, what?
John indexes we defined at the first part of the prediction.
Yeah, so that connection is basically when we define the Jones index, we used the object which is called the Jones star. So when we have the Jones index to be finite and the factors of this kind, only then we're able to construct this star of 2, 1 factors. And this star gives us these projections, which satisfy these very nice relations. And we need these relations to make this connection here. And because they also look very much like, it was surprising how much they look like the Markov relation for invariants of braids. And that's where they got the idea. So anything else? This is about it. I am done.
Okay, thank you. So more questions, please.
We also discuss S infinity group and
I'm sorry. Can you type it? Your voice is sort of muffled.
we also discuss S infinity group and it's interesting to see again how it appears in the story.
I apologize. I really cannot hear you. The voice is very muffled. If you could just please type the question, I could read it in the chat.
Well, Vladislav, if I understood your question correctly, if you're asking about the S infinity group, if I'm not mistaken, this is not the only choice. We can take any group with infinite conjugacy classes and then form the respective von Neumann group algebra, and we come to one factor. This is not the canonical choice for the group.
I mean, yeah, there are different factors, but we choose the hyperfinite case because it satisfied an additional property. I think it was the faithfulness of the trace property that is satisfied, which is why we chose that. And it's also very nicely represented because every such group, it gives us just one type of factor, the one that is isomorphic to the S infinity factor. And that was the object that was worked on solely because of some very nice representations. I'm not exactly sure what the fine detail of that is, but yeah.
Okay, thank you. So more questions, please. So if there are no more questions, then we thank the speaker. Thank you, Riya.
Thank you so much.
Our next meeting will be after the holidays, sometime in the middle of January.